Okay, time for another video. This is a global atmospheric change video. So I want to start out by talking a little bit about carbon dioxide as a heat trapping gas. And what we mean when we say a heat trapping gas is that basically these are gases in our atmosphere that absorb heat radiated from the surface of the planet. So Venus is incredibly hot because 96% of its atmosphere is CO2, and CO2 is a heat trapping gas. So what that means basically is that when you think about electromagnetic radiation coming to the Earth from the sun, so up here in the corner I'm going to draw a sun, and then down here we're going to have our Earth. Whoops. Sorry, I've got something stuck on my screen here. Down here we've got our Earth. So as this radiation comes through the atmosphere, it gets filtered out. So you get less and less as it gets closer and closer. So basically, when you think about electromagnetic radiation, we talked about this, you have the entire electromagnetic spectrum, from gamma rays on the one end, really high energy waves, to radio waves on the other end, really low energy ones. And we talked about frequency and wavelength and all of that. Well, a lot of this gets filtered out, especially the high energy ones. And what ultimately gets through is mostly like ultraviolet and visible, and some infrared. There's some other stuff that gets through too, but those are the main ones to get through. We have a lot that gets filtered out. And then what electromagnetic radiation does is when it bounces off a surface, so it's basically, I say it bounces off a surface, but it basically is absorbed and then re-emitted by the Earth. And when it's re-emitted in a different form. So it's the same thing when light travels and bends and reflects. What you see is, if it's visible, is a different wavelength, often a different color. That's why, why the sky is particularly blue, why you see red sunsets. It has to do with the wavelength in which you're seeing, with what light is bended through the atmosphere, and those types of things. They give you those different colors. So ultimately, what we see is most of what's being radiated is IR. IR is what you feel is heat. When you sit next to a fire, the heat that you feel, that is infrared radiation. It's not visible to your eye. Only part of the electromagnetic spectrum is visible to us, and that is what we call the visible spectrum, obviously. Although IR is visible to some animals that are nocturnal. So you can hunt at night, you can actually see the infrared radiation given off by your prey, that type of thing. So this infrared radiation is then absorbed by these different atmospheric gases that are capable of absorbing infrared radiation. Not all gases are capable of absorbing infrared radiation. For instance, O2 is not capable of absorbing infrared radiation. N2 is not. It has to do with the structure and all of that. We're not going to go into that. That's way too advanced of chemistry. But these are CFCs, was something we'll talk about. Those are man-made. The rest of these occur naturally in the atmosphere. Of course, we're often changing the concentrations of ones like this. Water is just naturally cycling. We could at certain times have more water vapor in the atmosphere at any one time. All right. Especially as the planet warms, more water will go into the atmosphere. Higher temperature, right? More of it evaporates. But the amount of water on the surface of the Earth is just constant and is just cycling. But some of these others were actually, releasing from areas that they wouldn't normally be in the atmosphere. We're releasing them. If we're burning fossil fuels, obviously we're creating CO2 that was tied up, if you will, in carbon compounds in the fuel. So this is one of the real concerns. No one really debates that CO2 is a heat trapping gas. That's just fundamental chemistry. That's not where the debate lies. So this is the concentration of CO2 as a function of year measured in Hawaii Observatory. And I've picked just a small segment of a bigger data set. And this is the full data set. And this is a more updated figure um, than um, some of you might have seen in slides that I've posted. But the trend is the same. The slides I post, I think, don't go up to 2020. Um, so what you see is that's why I want to make the point is that um, people will often be disingenuous in how they present data because they want to make a point. They have an agenda, or they're just not knowledgeable enough and shouldn't be presenting the data. Leave that to the scientists and the experts specifically within the scientific field. But I actually saw this type of data presented and presented in a way that says, it's up and down, it's up and down. How could we even be certain that it's increasing over time? This is back when this was the debate, was the major part of the debate for climate change was CO2 really increasing? And we know why it goes up and down. That's due to seasonal variations. Okay? Plants in the summer are more active, they're photosynthesizing, therefore they're taking in CO2, and CO2 levels are lower. So these are summer measurements. In the winter, they're dormant, they're not photosynthesizing as much. These are winter measurements. So we know that cycling. And then when you look at the entire data set, it becomes fairly clear that CO2 is increasing. So that kind of debate has been settled. We have tons of data. We've got measurements made in different places. We measure it in upper atmosphere, lower atmosphere, all sorts of things. So then it becomes about the temperature. Was the temperature truly increasing? And this is where a crux of some of the debate lies. Now you look at a figure like this and you say to yourself, well, looks pretty clear the temperature's increasing. But this is only a short period of time when you think about it on a global scale. And when you think about temperature on a global scale, here we're going back to the year 1000, there are figures like this, going back even further, obviously age in thousands of years, are looking at 160,000 years ago. So when you look at this, it looks like it's increasing, right? When you look at something like this, well, it seems to be a lot more fluctuating. But this is the part that concerns scientists over here, the rate of change. It's not so much the temperature as the rate of change. So there are periods in our global history in which temperatures were higher than maybe they are now. And you could see the huge fluctuations. So people say, well, what's the big deal? We're up and down all over the place. This was, 20,000 years ago, right? That we saw this massive change. So here now, you can't even see what we're talking about in terms of figures like this. This is only 1,000 years ago. So this is a fraction of this figure. And this one, of course, you can't even see in there. So this is part of the argument. Well, temperatures are all over the place in our geological time scale. But when scientists go and model this data, they're able often to figure out some of why you're seeing these trends. And they can look at things like changes in solar radiation. They can look at things in changes in Earth's temperature, currents in the ocean, all sorts of stuff like this, much of which is beyond me in terms of this modeling. And they can explain a lot of it. And there's been ice ages and warm periods throughout our geological time. This, once again, is what concerns scientists, is the rate at which it's changing. Okay, over such a small time period. You say, well, look how fast it changed here. But look at this. This is thousands of years, right? This is, right? We're talking maybe 50 years, okay? 1950 to 2000, that you're seeing this rapid increase, right? This is the real concern. Now, it's this time scale wise. This is only, 0.8. And this is really departures from average temperatures right here. That's what this is. Trying to demonstrate what has happened recently. And here's your temperature scale over here. This is CO2 concentrations over here. Here's your temperature scale over here. So here you're looking at, a bigger temperature change. You're looking at more like 10 degrees here. But you're talking about, 10,000 years, right? And that's the real key. This is measured by air bubbles trapped within ice cores. So obviously what we do we can do is when there are different temperatures, that means there's different amounts of gases in the water than in the air. Just like if you put a pot of water on the stove and you start to heat it up, the gases that are dissolved in that water will start to escape to the atmosphere. Okay? So if you were to freeze that pot of water at different temperatures, you'd have a different proportion of gas molecules in that water. And you can look at the CO2 levels to figure out, okay, you can figure out how much CO2 was in the atmosphere based on how much was in the water, because the CO2 distributes itself based on temperature. And those are known parameters for particular gases and substances. These are known parameters that can be looked up. So people can make those determinations from getting ice cores and stuff like that. And you see that the temperature and the CO2 concentration mimic each other. And a lot of the modeling has shown that in most cases, the temperature follows the CO2 increase, meaning the CO2 is causing the temperature increase rather than vice versa, because obviously, like what I just said, higher temperature will result in a higher CO2 concentration in the air. And there are cases in our geological history where that happens, but based on their modeling, they determine that most of the time it's the reverse of that, that the CO2 is causing the increase. This is known as the hockey stick model, and this is once again what's disturbing to a lot of scientists. This shows you gases. We have two different scales, parts per billion for methane and parts per million for these other two gases, CO2 and 2. And as you can see, these mimic that temperature change. So these gases are increasing tremendously, and that's part of the problem, and we've learned about that from our fossil fuel section, why they're increasing. So one of the concerns, too, is how long these gases stay in the atmosphere. That's called the residence time. While methane is only about 10 years, carbon dioxide can stay in the atmosphere for 100 years or more. So that is a bit of a concern there, and that's all we just define residence time as. Positive feedback is another concern that results when we deal with global atmospheric change, because what happens is you get an enhancement or amplification of the effect by its own kind of process. And I'm going to explain that here through albedo. Albedo basically is the amount of the sun's rays that are reflected and scattered back into space. So you can see the albedo changes based on kind of the color of the surface. Something like snow or ice has a large albedo because it reflects it. Something like forest land, which is fairly dark, absorbs mostly. So the positive feedback is as we melt snow and glaciers and things like that and uncover just, land that's below that tundra land, that land's going to absorb a lot more. So as the temperatures rise due to climate change, we melt the ice caps. The positive feedback is the melting of the ice caps changes the albedo, which further warms the planet. That's the idea of positive feedback, and that exasperates the problem. So there are uncertainties. We're not confident about everything, of exactly the amount of warming, what exactly our CO2 levels are going to be in the future, because right now we're not really slowing things down much. The population is growing. Third world countries are developing more. This is a real concern. Oceans will absorb some CO2. We have an idea of how much they'll absorb, but there's a little bit of uncertainty there. But that's actually not necessarily always a great thing, because CO2, when absorbed into water, forms carbonic acid. This lowers the pH of the ocean. This is an acid. This lowers the pH of the ocean. This has a bleaching effect on coral and other organisms that rely on, shells and stuff like that, clams and things like that. So the acid effects is negative. Clouds can actually reflect and actually have a cooling effect. As you put more water vapor into the air, you form more clouds. Vegetation will take up some CO2, but there are limitations to that. So there's lots of effects. Effects on animals, species will go extinct. Forest will be affected. Economic effects. Uneven heating, which results in more violent storms and more frequent storms. Sea level rises, which will sea level rises as ice caps melt. This will actually displace a lot of people. that live along the coast. Climate change, spread of diseases now, uh, pathogens and things like that can occupy um, greater regions of the globe that were too cold for them before. Agriculture changes as climate changes. You can't grow certain crops in certain places. There are some positive things that can happen. You might be able to grow a crop that you couldn't grow before. So you can look at some of these effects. This figure is available to you. I want to say one last thing is that within the scientific community, there was a couple studies done recently about looking at the top journals in the field that publish climate change data and the top scientists that publish in those. And there is a 97 to 99% consensus among scientists that work in this area and publish that human input of carbon dioxide to the atmosphere is affecting our climate significantly. That is really not debated much in the scientific community anymore. There are still a few percentage of scientists that are on the other side of the aisle, and that's fine. There's always going to be debate in science, but I wanted to impart that to you that there isn't, much debate. There is a fairly strong consensus um, that this is a real concern, and the debate is more in the political realm and on talk shows and things like that. Okay, the other part of this video is ozone depletion. Now, as you know, ozone is naturally occurring throughout the stratosphere. It forms the ozone layer, and it's an effective filter for us. So some of the things that have happened with depletion is that a bunch of scientists did some work, but the ones that really did the Nobel Prize work were Molina, Rowland, and Crutzen, and they were able to really figure out what was happening. We were noticing the ozone was depleting, and a hole was forming, and they kind of delineated what that was, and I'm going to explain that to you. And since then, the hole's been recognized. We've had various, we had the 1987 Montreal Protocol that addressed it, and then we've had amendments since then. Beyond the 1990 amendments, there's been Copenhagen, I think, and Stockholm, different conventions that have had multiple amendments dealing with this. Okay, so first we need to talk about normal ozone depletion. Ozone normally cycles. Okay, when it absorbs that UV light that it's protecting us, it actually breaks apart. That's the way it absorbs it. The energy goes into breaking the bond. That means the ozone is gone. But O2 also absorbs UV light and forms 2 oxygen also. And we can actually combine these singlet oxygens here with O2 and form ozone. Okay? Ozone can actually react with a singlet oxygen and form 2O2. So this is constantly happening and constantly cycling. It's estimated the average ozone molecule only lasts about 20 minutes in the stratosphere, but then a new one is formed. So the concentration is fairly constant, okay? And of course, that ozone in the stratosphere is cycling. It's not stationary. It moves, from one part to another. It stays in that area, but the ozone that's over Tennessee isn't the same ozone molecules all the time. There's movement of that air. Realize that. So these scientists started to realize that we were putting chemicals into the atmosphere, and I'll talk about these at the end of the video. Chlorofluorocarbons. This is just one chlorofluorocarbon. We call that chloro, chlorine, fluoro, and carbon. This is the simplest of them. And what happens was that when it gets up there to the stratosphere, it absorbs UV light and produces this chlorine, and that's the element chlorine, and a single atom of chlorine, which has 7 valence electrons. So when you think about your Lewis structure, I call it Lewis structure, I didn't call it that for you guys, but you think about the dots, it has 7, right? You're supposed to pair them. It's going to have one single dot. That's what this is just showing, that single one. Anything that has a single dot means it has an unpaired electron, and it's very reactive. This acts as a catalyst, and what it does, it catalyzes the destruction of ozone, forming this right here. What's key is this cycles around and reforms the chlorine. The definition of a catalyst is speeds up a reaction, but it can be used over and over again. So this is what happens. The chlorine just keeps cycling, and the chlorine just keeps destroying ozone. It's estimated that a single CFC molecule will destroy 10,000 ozone molecules before it kind of reacts with something else in the atmosphere and is pulled out of the cycle. It Could be some other gas. So all idea here is the net reaction is the destruction of ozone, and it's a catalytic destruction of ozone. Ozone normally cycles like this, but it's not a catalytic destruction of ozone. This is what the scientists showed, and this was one of the famous figures. And basically, it's supporting the evidence of their mechanism. We call this the mechanism, explain exactly how it happens. When you understand the mechanism, you can explain a lot of what's going on. That's one of the keys to delineating a mechanism. That when CLO increases, ozone decreases, and that's exactly what the mechanism predicts. This shows you the ozone hole over several years. This is an old figure, but still, what you're looking at Dobson units, just think about that as the concentration of the ozone. The red means going to be your ozone layer is going to be a greater concentration. When you get the purple, it's really low, and you see here in 97 compared to 79, big decrease in the ozone layers, ozone. And this shows you the hole peaked at about 2006, and it starts to recover a little bit. And this, the ozone amounts, and you can see it's lowest at 2006. So the actual hole only occurs over the South Pole, the Antarctica regions. It's because of these special weather conditions that occur. So you get this months of darkness, because when you're right at the pole, you have very little sunlight in the winter, right? So you have long periods of darkness. You have really low pressures, really cold temperatures. You get these special clouds that form as a result of condensation. Because of the darkness, the chlorine that's released from the CFCs, it forms the chlorine molecule now, and that gets stored and collects over time. And then what happens in the springtime, the chlorine actually reacts with the UV light, producing this all at once, and that destroys a bunch of ozone all at once. So much so that in the areas like New Zealand and Australia, they're told in the springtime and early summer, if you go outside, wear long sleeve shirts and stuff like that. There is documented higher incidence of skin cancer in those regions. So we used CFCs because they had super desirable properties. They were low viscosity and low surface tension, which means they were great. They were used in refrigerants. Okay, refrigerators, air conditioners. They were non-toxic. They were non-reactive. Where does it say that? Chemical inertness means non-reactive. They were perfect. So the people working with them weren't exposed to toxic chemicals. There weren't concerns about explosions and fires. They were perfect. But because they were inert, what happened was when they're released, they would get up into the stratosphere because they wouldn't react with anything in the troposphere. And then they would destroy the ozone, release the chlorine. So we've come up with some alternatives over time, and we're still working on alternatives. But some of those alternatives are potent greenhouse gases, and that's part of the problem. So we got to keep working on solving that problem. This was the Montreal Protocol, and happened in 87, so you can see we had a huge drop in the amount of CFCs. However, there were some developing countries back then that were still using them, but we've come a long way, and the ozone layer is starting to recover. And this is one of the success stories. We have to be diligent and insist on helping countries that are going to still try to use these compounds to continue to replace them with other compounds. So that's the end of this video.